Hello friends, in this part of the program I am going to discuss Stern-Gerlach experiment, electron spin and vector model of atom. Now, magnetic moment mu L associated with a charged particle having charge q and orbital angular momentum L is given by mu L is equal to q by 2m gl times L vector, where gl is g factor for orbital motion and gl is equal to 1, and gyromagnetic ratio for orbital motion is defined as the ratio of mu L and L, that is mu L by L is q by 2m. Now, you see there is a charged particle in an orbit and then the orbital angular momentum referred to center is L and L is equal to r cross p. Now, L is perpendicular to the plane of the orbit and has magnitude L is equal to r p is equal to m v r. Now, for central force, torque is r cross f is 0 and L is conserved, and the current associated with the orbiting charged particle is I is equal to q over t, and then you can easily see that it is proportional to L, and now you define magnetic moment as current times enclosed area. So, this is q by 2m into L. This is a very important result, that the magnetic moment associated with a charged particle is proportional to the orbital angular momentum. Now, in vector notation, mu L vector is q by 2m gl times L, gl is equal to 1. Now, you must note that above this relation has been derived for circular orbit, but this holds even if orbit is not circular, but corresponds to angular momentum L. Now, Bohr magneton. For an electron in orbital motion, mu z you can very well see is proportional to Lz. I told you that Lz is quantized. So, mu z is proportional to ml, and then you define Bohr magneton as mu b is equal to E h bar by 2m, and it is 9.274 into 10 to the minus 24 joule per Tesla. So, we have mu z is equal to minus mu b times ml. Now, you can appreciate the fact that Bohr magneton is a unit in which magnetic moments of elementary particles are measured. Now, we discuss interaction of magnetic moment with magnetic field B. The potential energy is U and it is equal to minus mu dot B is equal to minus mu b cos theta, and torque is tau is equal to mu cross P. Now, the force is minus grad of U, and then if the field is homogeneous, force is 0, but if there is inhomogeneous magnetic field along z direction, then particle with magnetic moment mu z experiences the force F z is equal to mu z d d z of B z. This is the result that we are going to use. You appreciate the fact that the force on the particle is proportional to the gradient of the magnetic field. Larmor frequency. Now, atom placed in a uniform magnetic field B experiences a torque dl by dt is equal to minus mu b by h bar as L cross B. This is the basic definition, that the rate of change of angular momentum is equal to the applied torque. Now, when the B is along z direction, L square and Lz are constant, because you can very easily see that d dt of L dot L is equal to 0 and B dot dl by dt is equal to 0. It means L square and Lz both are constant. Further, you can easily show that Lx is equal to a cos omega b t, Ly is equal to a sin omega b t, and it means L vector precesses around magnetic field with Larmor frequency omega b is equal to mu b by h bar. Essentially, we are showing that placed in a magnetic field B, magnetic moment precesses around the vector B. Now we talk of spin angular momentum. One may think that total angular momentum of a particle is made of orbital angular momentum only, but Stern-Gerlach experiment shows that this is not the case. Particle may have spin angular momentum S in addition to orbital angular momentum L. Surprisingly, S is not equal to 0 even if particle is at rest. It has been shown that S is intrinsic property of a particle. Now, can we explain spin angular momentum classically? No, we cannot. Spin is one more degree of freedom associated with angular momentum which cannot be explained classically. Now, Earth orbits around Sun with some L and it also spins about its axis. Can we say by analogy that in an atom, electron orbits in a circle with some angular momentum and spin corresponds to electron spinning about its own axis passing through its center? No, this is not the correct picture because electron size is almost 0 and any classical model which views electron as a spinning charge distribution about its own axis is incorrect. You cannot separate spin from electron as you cannot separate charge from electron. Same is true for other particles with spin. Spin angular momentum is intrinsic property of a particle which can be explained by quantum mechanics only. You just cannot explain it by classical mechanics. Now, this is Stern-Gerlach experiment. You see in the slide, a beam of neutral silver atoms is subjected to inhomogeneous magnetic field in a transverse direction. This is the basic arrangement. Now, silver atom has a nucleus and 47 electrons. 46 electrons form a spherically symmetric electron cloud with 0 orbital angular momentum. Angular momentum of the 47th electron is also 0 because it is in the 5s state. For atom as a whole, therefore, L is equal to 0. From the relation mu L is equal to q by 2m GL times L, magnetic moment of silver atom in ground state is 0. Now, silver atom experiences a force Fz is equal to mu z ddz of Bz. In Stern-Gerlach experiment, deflection due to Fz is measured. So, effectively it is a measurement of magnetic moment mu z. This is the point to be noted, that basically we are trying to measure mu z. If origin of magnetic moment is solely from orbital angular momentum, it is clear that measured deflection should be 0, but what is seen experimentally is quite different. This is what you see. Experimental results can be explained only if somehow mu is not equal to 0, even if L is equal to 0, and mu z takes only two different values. Classically, for any mu not equal to 0, continuous values of mu z from minus mu to mu should be possible. That means, we do not get results as we expected from classical physics. Now, the results of this experiment can be explained only if, in addition to orbital angular momentum, spin angular momentum S also contributes to total angular momentum and to total magnetic moment. And then magnetic moment associated with the spin S of electron is mu s, then mu s is E by 2m Gs times S, and Gs is G factor for spin. Only two values of observed deflection means that Sz can take only two values. Agreement with observed deflection values is achieved if Sz is equal to plus minus h bar by 2 and Gs is equal to 2. Only two possible values of Sz is an example of space quantization of angular momentum. This is analogous to Lz is equal to mh bar for orbital angular momentum, because m takes value minus L to plus L spaced by unity. What you see in the diagram is quantization of orbital angular momentum. You can very well see that the magnitude of this is fixed, it is root L into L plus 1 by h bar. For L is equal to 2, it is root 6 h bar, but its projection on z axis can take values only minus 2 h bar, 2 plus 2 h bar spaced by unity. Similarly, the spin is quantized. Now, the spin has the magnitude root 3 by 2 h bar and its projection on z axis are only minus half h bar and plus half h bar. Now, what is the significance of Stern-Gerlach experiment? It points to the existence of spin angular momentum S for electron. Magnetic moment associated with the spin S of electron is mu S is E by 2m Gs times S vector, Gs is equal to 2, and spin S is space quantized, Sz is equal to plus minus S bar by 2, and mu Sz is equal to plus minus mu B. That is, Z component of magnetic moment of electron due to spin is plus minus 1 Bohr magneton. Now, we talk of total angular momentum. Total angular momentum J is defined as J is equal to L plus S. Why total? Because S is in addition to L. We had L because orbital motion, now we have also S which is spin motion. So, total J is L plus S. Now, like L and S, J is also space quantized. Operators J square and Jz are commuting operators and can be known simultaneously with precision. Quantum numbers used for total angular momentum are J and M, and J square takes the values J into J plus 1 h bar square, and Jz takes values only m h bar. For an isolated system, possible values of J square and Jz are J into J plus 1 h bar square and Jz is equal to m h bar. Moreover, 2j is integer for a given j, m can take 2j plus 1 values, m is from minus j to plus j spaced by unity. This is what you see is the space quantization of j is equal to 3 by 2, and mj can take all the values from minus 3 by 2 to plus 3 by 2, and its magnitude is root j into j plus 1. Now, we talk of vector model of atom. Vector model is an extension of Bohr-Sommerfeld atom model. Bohr model could not explain fine structure of spectral lines even for simple atoms. Essential features of a vector model are quantization of orbital angular momentum, originally called space quantization, and introduction of spin angular momentum. We have already talked about quantization of orbital angular momentum. Originally, in vector model, it was introduced in an ad hoc manner, but later full quantum mechanical treatment of angular momentum revealed that L square values are restricted to L into L plus 1 h bar square. Further, for a given L value, there are 2 L plus 1 allowed projections m h bar of L along z directions, m is equal to minus L to plus L spaced by unity. Now, classically L is equal to R cross P is known precisely because momentum and position can be known precisely at the same time. Quantum mechanics forbids this. So, only commuting operators L square and Lz can be known precisely at the same time. Existence of spin was pointed out by Stern-Gerlach experiment. For electron, S is equal to half, and space quantization of spin means allowed values of S square are S into S plus 1 h bar square, and the projections of Sz are ms h bar, and ms goes from minus S to plus S spaced by unity. For total angular momentum, J is equal to L plus S. Quantization rules are J square is equal to J into J plus 1 h bar square, and Jz is equal to m h bar. Now, we ask, what are the possible J values for a given L and S? Now, J varies from L minus S modulus to L plus S, with interval of unity. For example, if L is equal to 1, S is equal to half, then J is half and 3 half. Thus, various quantum numbers used in vector model of atom are N, L, ML, S, MS, J and M. N is total quantum number, it takes integral values 1 to 3. L is orbital angular momentum. For a given n, it may take any integral value from 0 to n minus 1. Conventionally, small s, p, d, f correspond to L is equal to 0, 1, 2, 3 and S is a spin quantum number. For an electron, it is half. For a system of 2 electrons, spin quantum number S takes values 0 and 1. Small j is total angular momentum quantum number, it takes values 0, half, 1, 3 half etc. 2j is positive integer. ML is magnetic orbital quantum number, MS is magnetic spin quantum number, Mj is magnetic total quantum number, it is ML plus MS. So, friends, we saw that Stern-Gerlach experiment pointed out to the existence of electron spin. Now, even at the cost of being repetitive, I would say that ultimately how exactly the spin idea came. You see, when you have a magnetic moment placed in a magnetic field and it experiences a force, then the force can come only because there is a magnetic moment. Now, if the spin were not present, then we have already seen that magnetic moment was absent. So, the question is, experimentally we did get the deflection. From where it came? It must have come because of the interaction of magnetic moment with the inhomogeneous magnetic field. Now, from where did the magnetic moment come? It could not have come from orbital angular momentum, because we have already seen that this was in the S state. But this is a fact that there was a deflection, and the deflection can come only from magnetic moment. So, that means magnetic moment should have some more origin other than orbital angular momentum. That is why it was thought that the orbital angular momentum is not the complete story. We must have some more another kind of angular momentum, and that was named as spin angular momentum. Further, even at the cost of being repetitive, I would say that why only 2 values of spin came? It came because only 2 values of deflection were obtained. So, we have a picture now that we have a spin angular momentum which is very different from classical orbital angular momentum. It is quantized in the sense that its z value can take only 2 values which are plus h bar by 2 and minus h bar by 2. Now, why they are h bar by 2 and minus h bar by 2? Because the agreement with the experimental results demanded that these sz values should have been only 2. So, this is the way of putting the space quantization of spin angular momentum. We have already seen how the L, that is the orbital angular momentum, was quantized because their z values were mh bar. Now, we have the situation in which you have 2 types of angular momenta, L and S, that is orbital angular momentum and the spin angular momentum, and both of these momenta are space quantized, that is their z values cannot take all possible values, but only some specified values. Lz is equal to mh bar and Sz is equal to plus h bar by 2 and minus h bar by 2. This is a result which is just not explainable from classical physics. So, it is here that quantum mechanics is coming into play, and without these you cannot explain many features of hydrogen atom and other atoms. So, this is the whole idea, that how you see the atom, how you look at the atom, and how you describe the things which are happening at the atomic level. I have seen that some students do not feel quite comfortable with the idea of a spin, because it is non-zero even for a particle which is under rest, because orbital angular momentum L is r cross p, and when p is equal to 0, that is particle is at rest, then L is 0. So, they expect that for a particle at rest the angular momentum should be 0, but with a spin it is not 0 even for a particle at rest. They should think on these lines, that spin is something which you just cannot separate from the electron, as you cannot separate charge from it. It is a intrinsic property of the electron. This is a very important point which must not be lost sight of, and one must always think that spin is always and always associated with electron, you just cannot take away from it. So, friends, in this part of the program we talked about spin of electron, and as you will see in subsequent lectures, that spin plays a very important role in describing various properties of electrons, and spin is something which we cannot explain from classical physics. It is inherently quantum in nature. So, today you just got exposed to this idea, and it should be with you in times to come to appreciate fully all aspects of atom. Thank you.